All right, guys, so what we're going to be looking at here is we're going to be looking at this last topic when it comes to antiderivatives and how they can help us out. And this topic that we're going to be talking about are what are known as particular solutions. When we were talking about slope fields, we talked a little bit about how we can know based on the fact that we've got x's and y's mixed together in a fraction, or in a derivative, excuse me, that we can know at least kind of what the original function looks like by drawing a slope field to help us understand a little bit better what the function might look like. So on the last assignment, we had slope fields that looked like this. We drew a little slope field and we said, okay, if it was above the x-axis, it might end up looking like that. We didn't know. We just knew that it kind of had that behavior. And we knew that if it was below the x-axis, maybe it ended up looking like that. But we did not know where to draw our graph. And it wasn't necessarily a function because it wouldn't always pass the vertical line test. But we knew that it at least had these behaviors as we move from left to right, up and down. We could see the different things that were going on based on the fact that we had this slope field. The problem was, just like I said before, is it didn't tell us what the original function was. And one of the big issues that we had where we didn't know what the slope field or what the original function was is that plus c doesn't tell us how far the function has been shifted up or down. It just says, okay, there is a constant number. Maybe it's above the x-axis. If it's a positive plus c, maybe it's below the x-axis. If it's a negative plus c. But unfortunately, we do not know, based on the information we had before, especially with a slope field, about what the original equation may look like. And so it tells us some characteristics. Like, again, the slope field tells us some of the things we need to know about the original function, but it doesn't tell us everything, okay? Now, when we were doing those initial value problems, the problems where the x's and y's weren't mixed together, you knew the derivative, and you took the antiderivative, and then you were given one additional piece of information. And that one additional piece of information that you were given that allowed you to find the plus c in those problems was a point that existed on the original function. The reason why that helped us so much is once we knew that, it allowed us to pin down where the graph was. So there wasn't any longer a shift up and down. We knew that the graph had to pass through this point, and then once we knew that, we could find out what the original function was because we knew how much it had been shifted up or down by, okay? The way that we used it, if you remember, is we took the antiderivative, plugged that point in for x and y, and then we solved for c and put that c back in so that we could know how far the graph had been shifted up or down. So here's kind of, and what I'm going to do here is I'm going to be hopping back and forth between this screen and the next one, okay? But if we knew that dy dx equals x divided by 2y, so notice again, we've got x's and y's mixed together here, and this is a big thing that we know, and that the point 2, 1 existed on the original graph, then what was the original equation? Now, a couple things I do want to call to your attention. Number one, you need to know that not all of these things that we're going to get are going to be a function. And that's okay. There's nothing wrong with that. That's why it says original equation rather than the original function. Okay? Number two, what we're going to do in order to solve these problems is we are going to follow some steps. Okay? And so I'm going to show you these steps on the next screen, and we'll go back and forth to them over and over and over. Okay? So step number one, what we're going to do, and this will make a little bit more sense about what we're talking about in just a second, is any term that has an x, we are going to move to the right-hand side of that equation that we just saw for the derivative. And anything that has a y, we're going to move to the left. And we can only do that by multiplication and division. We can't add or subtract anything to get it from one side to the other. And that's a very important thing that you have to understand, is we can only use multiplication and division to do this. And again, it might not make a ton of sense right now, especially step number one. You look back at this problem, you're like, why, if I had dy dx equals x divided by 2y, would I ever want to do that first step? But let's do it anyway to make sure that we're okay. Now, any term that we're talking about includes both dy and dx. Those are not excluded from this just because that's a little bit different than what we've talked about before. So what we're going to do is this dx, notice, is on the left-hand side. We are going to multiply that over to this side. Kind of like when we did u substitution. It's different here, but we're multiplying that over, okay? So I've got like dy equals x times dx divided by 2y. And then this term on the bottom here needs to move over to the left-hand side because it's got a y in it. So I get 2y dy equals x dx. So that's the first step that we take when we're trying to solve these problems. They're called particular solutions, but that's always the first step every single time. If you're looking for the original equation, that's the first thing that you need to do. Okay, so there's step number 1. Now, step number 2, as you can see over here, is we are going to take the antiderivative of both sides of the equation. So here, I'm going to take the antiderivative of both sides. That's why we moved the dy, kept the dy over on the left-hand side, and we moved the dx over to the right-hand side, so that these looked like something we could take the antiderivative of. So in this case, I get y squared, and technically it's plus c. I'm going to write it a little bit different. We'll talk about y in just a second. Y squared plus a constant number is equal to x squared divided by 2 plus a constant number. And it's a different constant number. So in this case, there is my antiderivative. Now, you'll notice over here on step 3, it says don't forget to write the plus c. The plus c is so important in these problems because if you're taking the AP exam and you forget to write plus c, you can actually earn no more points after this point if you forget the plus c. Now, you might be asking, okay, well, what plus c do I write? Like, there are 2 of them there. Technically, I could subtract this constant from this constant, and they're different numbers, but a constant number minus a constant number still gives us a constant number. So when we're doing these problems, you just take the antiderivative, and although there are technically 2 different constant numbers, we only worry about one of them because really there's just one constant number if we were to combine like terms. So that is step number 3. Now you'll notice on step number 3 there that we have something very similar to what we had when we were doing those initial value problems. The only difference is y is not just y, like in this case it's y squared. But that doesn't change how we do these problems. Step number 4, you can see it over here, is we have a given point and I need to know what the plus c is. So I take the point that I'm given, where x equals 2 and y equals 1, and I put that in for x and y. So this step is very similar to what we did when we were doing initial value problems. So I get 1, whoops, that's 2 squared divided by 2. 1 squared is equal to 2 squared divided by 2, which is just 2 plus c. So c in this case is equal to -1. So over here, like you see, we find out what c is, and that's step number 4. Step number 5 is what we're going to do is we're going to take that c and we're going to plug it back in like we did with our initial value problems. Oops, this is x squared divided by 2. There we go. That's what was throwing me off. So I've got y squared is equal to x squared divided by 2, and we just found out our c is -1, so I'm going to put -1 right there. Now, the other part of step 5 that it says over here is we have to solve for y. In other words, we got to get that y by itself. So it's an additional step that we have to take in these problems that are different from the initial value problems. So to get the y by itself, in this case, I take the square root. So I get y equals, and technically it is plus or minus, we'll talk about that in just a second, the square root of x squared divided by 2 minus 1. Now, if I leave it as plus or minus, technically I haven't quite finished the problem yet, because you'll notice it says y equals either positive or negative. Well, a square root is always a positive number, so I have to figure out whether or not I'm going to get a positive or negative when I plug in any x value. And the way that we do that is we go up here and we look at what the y value is. Notice that that is a positive number that we were given initially. In order for that to be positive, the square root part is going to give me a positive, so the rest has to be positive as well. So I can get rid of the negative because that is not what needs to be true in order for my y value to equal the square root of x squared divided by 2 minus 1. If that were -1, then what we would do is we would just make this negative down here and everything else would stay exactly the same. And what we've done is we have discovered what the original equation was based on the fact that we know the derivative and we have a point that exists on the original function. Okay? So we kind of talked about why we did all these things. So if you don't know exactly what we put there, that's totally fine, because we're going to do another couple examples and hopefully it'll just kind of make sense. So here's another one, okay? I've got dy dx equals y times x squared, and I got the point 0, 1. Okay, notice it's just been simplified a lot here. So step number 1 is every single time we move every term that has a y over to the left-hand side, every term that has an x over to the right. And in general, you want the dy and the dx to be off to the side. So I'm going to divide the y over to the one side, and then I multiply the dx over to the other side, so I get x squared dx. That's step number 1. Step number 2 is we are going to take the antiderivative of both sides. So in this case, when I take the antiderivative of 1 over y, it's the ln of the absolute value of y is equal to x to the third divided by 3. And then technically, my third step comes in here. I have to remember my plus c. So now I've taken my antiderivative. Step number 4 is I take my x and my y values and I plug them in to my equation that I have so that I can solve for c. We've talked about this before. The ln of 1 is 0. It's about the only ln you really need to know. So I get 0 equals 0 plus c. And this happens sometimes. My constant is 0. So step number 5 is I take that, the ln of the absolute value of y is equal to x to the third divided by 3. Then I put plus 0, but I don't have to write that. So that now I put my plus c back in. But because this is a slightly different kind of problem, I have to talk about how I'm going to get the y all by itself. And the way that we do that in this problem is anytime we see an ln, what we do is we change, if we need to get the y by itself, we change from logarithmic form to exponential form. The way that we do that is we just say y is equal to e, which is the base number, to the x to the third divided by 3. And you would do that to everything that is over on the left-hand side of the equal sign. So whatever it was, we would just change it to that. And that, in this case, would be my particular solution. Again, these are very similar to initial value problems. They just have a couple additional steps because it's not just y, so we have to get the y by itself. In fact, you could actually use this method on initial value problems and you would get the right answer every single time as well. Now, a couple of things that people forget is if I had like e to the y equals like x squared minus 2, what we would have to do in order to solve for y is we would have to take the ln of both sides. In reality, what we're doing is I want to solve for y, but you can't solve for something when it's in the exponent of anything. So in order to move that out of the exponent, I need to be looking at a logarithm. When I do that, and you learned these last year when you were taking Math 3, that allows you to move that down, and then the ln of e is 1. So in this case, I'd get y equals ln of x squared minus 2. When we have the ln of y equals, we'll just go with x squared again, what we do is just like we did on the last problem, I just change it to exponential form. So I'd have y equals e to the x squared, and that would be changing it to get the y by itself. Now, if I had y to any number power, and this happens from time to time, let's say I had y to the 3/2 power equals x squared minus 4, and I needed to get that y by itself. What we do to get rid of the exponent to get the y by itself is you take whatever the number is and you just flip it upside down and take both sides to that power, and it will eliminate that fractional exponent. And that works no matter what. If I had y to the third equals x to the third minus 5, and I wanted to get that by itself, I could just take both sides. 3 flipped upside down is 1/3. So I could take both of those to the 1/3 power, and that would get rid of that exponent. And it works every time. Okay, so I've got x squared minus 4 to the 2/3, going back to what I was talking about before. So when we solve for y, those are some techniques that you can use to get that y by itself. Now, I will say on the AP exam, one thing that I want to call your attention to is a lot of times it's pretty hard to get the y by itself, and getting the y by itself is almost always only worth 1 point. And since it's only worth 1 point, to me, it's something that if you can do it, yeah, go for it for sure. But a lot of times it's just a lot of work for not a lot of points on the test. And we will discuss that more as we get closer. Okay? So let's look at this one. Okay, let's say I had dy dx. Let's follow our steps real quick. Let's move the y's over to one side. So I'm going to have 1 over e to the y dy equals x dx. And then step number 2 is we're going to take the antiderivative of both sides. Now, in order for us to take the antiderivative of 1 over e to the y, I actually have to make this e to the negative y dy. Notice I moved it to the top and I made the exponent negative. I've got x dx here. In order to take, so the antiderivative of x is x squared divided by 2 plus c. Okay? And then on this side, the antiderivative of e to the negative y is actually e to the negative y divided by negative 1. And it's just like a simple u substitution. Just trust me on that one, just in the interest of time. So there's my third step when I wrote the plus c. Step number 4 is I plug in the numbers that I have. So I take 0, e to the negative 0 divided by negative 1 is equal to 2 squared divided by 2 plus c. E to the 0 is 1, so I get 1 divided by negative 1, which is negative 1, is equal to 2 squared divided by 2 is 2 plus c. So c in this case is equal to negative 3. So now what I do is I take that c and I plug it back in. So I've got e to the negative y divided by negative 1 is equal to x squared divided by 2 minus 3. Then what I'm going to do is take that negative 1, because I got it, that was step number 4. And then step number 5, I plugged it back in, and now I have to solve for y. So I'm going to multiply everything by negative 1. So I get e to the negative y is equal to negative 1 times x squared divided by 2 minus 3. I got to get to that y, and the only way to do that is to take the ln of both sides. So I get negative y is equal to the ln of negative 1 times x squared divided by 2 minus 3. Then to get the y by itself, divide both sides by negative 1. So I get y equals all of that. And you can simplify if you want, but really there's no reason to. And I write that as my answer. Now, hopefully that made sense as we went through those a couple times. I know this is a little bit more complicated what we're looking at, but hopefully all that makes sense and you feel confident about it. So if you have any questions, please let me know.